Hello everyone, so welcome to my video on the derivative of exponential functions. We've seen up to now the derivative of polynomial functions, functions with roots, functions with fractional exponents, but now we're going to take a look at transcendental functions. So among the transcendental functions, we're going to take a look at exponential functions here. In future videos, we're going to look at logarithmic functions, trig functions, sine, cosine, tan, among others. So today we're going to look at the derivative of e to the x. So in order to prove the statement that the derivative of e to the x is in fact itself e to the x, we require a couple of limits that we have to know. Okay. So the first limit that we're going to talk about is the fact that the limit, so as n goes to infinity, of 1 plus 1 over n, all this to the exponent n, is equal to e, which is approximately 2.718, so on and so forth. Okay. This is the definition, the limit definition of the number e. So this limit over here, I'm not going to prove, we're just going to assume it to be true. We're actually going to see this later in the semester. It's going to come back when we do L'Hopital's rule, and we'll be able to show that this is in fact a true statement. So for now, we're just going to use this limit. The actual limit that we want to prove is the following. So we want to show that the limit as h tends to 0 of e to the h minus 1 over h is equal to 1. This is the limit that we want to show. We want to show that this statement is true. Again, you could also prove this using L'Hopital's rule, which at this stage we don't know. This is something we would see at the end of the semester, but that's a bit of a cyclic argument, so let's prove this without using L'Hopital's rule. Let's show this to be true. Okay, and in order to prove this, we have to make use of this formula up here. So the first thing we could do is apply the substitution. So solution, this is we'll let h equal 1 over n. Okay. So we're going to substitute all the h's here with 1 over n. What that gives us is the limit as 1 over n tends to 0 of e to the 1 over n minus 1 over 1 over n. We want to show that this thing here is equal to 1. We can't use this, we want to show this. So from this over here, we have this. Okay, using this substitution. Okay, great. So the first thing that we're going to do is notice that the limit definition over here, we have n tending to infinity. So in order to get this, what we have to do is change this form. The idea is limit as 1 over n tending to 0 is equivalent to limit as n tends to infinity, because as n is going to infinity, 1 over n would go to 0. So it's equivalent to write the limit as n tends to infinity of e to the 1 over n minus 1 over 1 over n. Okay, so we're allowed to do this. Next, what we could do is we have a fraction divided by a fraction, so we could multiply by the reciprocal, giving us the limit as n tends to infinity of n times e to the 1 over n minus 1. Right, because if we flip the fraction on top, well, the term on top, we leave it as is, e to the 1 over n minus 1, and this fraction, the 1 over n, becomes n over 1. You're multiplying by n over 1, so, which is essentially just multiplying by n. So that's how we get this term here. And now what we could do is use the fact that here we're taking the limit of two terms which are multiplying, so we could take the limit of each term individually. But essentially, since we're taking the limit as n goes to infinity of e, by definition, we're still taking the limit as n goes to infinity. We could substitute or replace e with this term over here. There's different ways of doing this, but this is just among one of the ways. So instead of writing e, we could rewrite it as 1 plus 1 over n to the n in here. So this gives us the limit as n tends to infinity of n times, and instead of writing e, we're going to rewrite it with this limit here. 1 plus 1 over n, all this to the n. This part is e. But notice that the e was to the exponent 1 over n, so it's all this to the exponent. Let me put all this in square brackets. We'll put square brackets here just to differentiate. This is to the bracket 1 over n minus 1, all that in square brackets. Okay. So what you have to catch here is that the exponent n and the 1 over n, they cancel each other, because n times 1 over n is 1. And what we're left with is 1 plus 1 over n minus 1. So the 1's cancel as well. And what we're left with is n times 1 over n. N times 1 over n, this whole thing just equals 1. And this is the limit we wanted to prove. Okay, so here we have our original limit, definition of e. This is the limit that we just proved, that the limit as h tends to 0 of e to the h minus 1 over h is equal to 1. And we want to show that the derivative of e to the x, if f of x is equal to e to the x, then its derivative f prime of x is equal to e to the x. Let's go ahead and prove that. So proof. So we start off with f prime of x, and we write the limit definition. So the limit as h tends to 0 of f of x plus h minus f of x over h. Okay. So if f of x is e to the x, f of x plus h becomes the limit as h tends to 0. We replace the x with x plus h, giving us e to the x plus h minus e to the x. All this over h. Okay. So the next property you have to apply is one that we're used to doing it the other way. So it might be difficult to get to the next stage. But just keep in mind, we know that if we're multiplying the same base, x to the a times x to the b, when you're multiplying the same base, what do we do to the exponents? We add them. This is equal to x times, x to the a plus b. But here we're going to go the opposite way. So if we have an addition in the exponent, we could turn this into two terms and multiply them. So this is equivalent to the limit as h tends to 0 of e to the x times e to the h minus e to the x, all this over h. Okay, using this property backwards. Okay, so we have the same base, the e, we have two of them now, and we separated the x and the h. Okay, so we get to this stage. The reason why we do this is because now we're able to factor out an e to the x in the numerator, giving us the limit as h tends to 0 of e to the x times e to the h minus 1 over h. Okay. And now our properties of limits says if we have a multiplication, we could deal with each term individually. Actually, the e to the x here doesn't have a h involved, so we could actually just pull it out and treat it like a constant. This is giving us e to the x times the limit as h tends to 0 of e to the h minus 1 over h, which was the limit that we just showed previously, e to the h minus 1 over h as the limit of h tends to 0. This is just equal to 1. Okay, so this whole thing is just equal to 1. So 1 times e to the x is just e to the x, and we're done. We proved that the derivative of f prime of x is equal to e to the x. Okay, so there's not many examples we could do with this, but just a couple of warnings I wanted to give you. So example, first one, obviously if f of x, the function is equal to e to the x, we know that its derivative is f prime of x e to the x. This is what we just proved. But things you have to be careful for is if you have something like this, if you have f of x is equal to e to the pi, okay, it looks like it's e to the x. It's not, there's no x's involved. This is actually just a constant, so be careful. Don't fall for that trap. So although it may look like e to the x, its derivative here of a constant we saw from the constant rule. This is actually 0. The other thing I want you to be careful for is the fact that teachers may try to scare you. So if we ask you to find, we haven't seen higher derivatives yet, I'm going to do that in another video, but essentially if they ask us to take the derivative multiple times of e to the x, so something like take the derivative, the 10,000th derivative of e to the x. So this seems intimidating. This is the notation we use for multiple derivatives, so it's essentially like an exponent, but in brackets. This is telling us to take the 10,000th derivative of this function e to the x. Oh, sorry. The way I should write it is probably if f of x let's write it this way. If f of x is e to the x, we want to know what the 10,000th derivative is. So when we took the derivative of e to the x once, we got e to the x. If we take it again and again and again, so this seems intimidating, but it's just e to the x, and that's the final answer. Okay, so we saw the derivative of e to the x. What if it's not e? What if it's any other number? So let a be a positive constant, then if f of x is equal to a to the x, its derivative f prime of x is equal to a to the x. It stays the same, but there's this multiplication of ln of a. Okay, and we can see why this is true for e to the x. This is a more general version, because if f of x is e to the x, this is consistent with what we just proved, because if we replace a with the number e, 2.718, we have e to the x times ln of e. And we know from our log properties that ln of e is just 1, which is e to the x, as we just proved. Okay, so this is the more general version. Okay, I'm not going to prove this one here. We're just going to use it. We're going to prove it in a future video once we do a logarithmic differentiation and chain rule. I think both of those are required. But let's take a look at a couple of examples, because I want to show common mistakes that students make. So example, if we have the function f of x equals, let's say 5 to the x, this implies that the derivative of 5 to the x is, it stays the same. So this is what this is saying, a to the x stays the same, so 5 to the x. And then you're going to multiply by ln of a, so times ln of 5. Okay. And that's your answer, we're done. So a common mistake that students make is they often confuse x squared versus e to the x. Sorry, not e to the x, 2 to the x. Okay. So you have to be very careful. In this case, x squared is a polynomial, specifically a monomial, just one single term. Your x is the base. Here the x is in the exponent, it's not the base, so that's the main difference. Okay, so if you have exponential function where x is in the exponent and you have a constant on the bottom, then we could apply the property. So the derivative of x squared we saw in a previous video is 2x. This is power rule. You drop the 2, you subtract the 2 by 1. Whereas here, this is the exponential rule. We're using this one here, where its derivative is going to be, this stays the same, 2 to the x, and then you multiply by ln of the number 2. Okay, so make sure you catch the difference. Don't fall for these little traps. Another thing I just want to mention is that if we're given the function f of x equals x to the x, are we capable, or are we allowed to use this? Both no, because the rule says a has to be a constant. So here we have a function as a base, so you cannot apply the rule. Okay. This one here you can't do. Oops, I'm not going to put an x. It's a bit confusing, but we don't know the derivative yet. We are going to see this later on when we do logarithmic differentiation. Okay, but make sure when you're applying this rule here specifically, the base is a constant, it's a number, and x is in the exponent. Then you could apply it. Okay, so next, instead of looking at exponential functions, now we're going to look at logarithmic functions. So let a be a positive constant, then if f of x is equal to log base a of x, its derivative f prime of x is equal to 1 over x times ln of a. So this is just something you have to have memorized. I'm not going to prove this again. I'm going to wait till we get further along. Once we do logarithmic differentiation, then I'll show you the proof. But for now, we're just going to look at examples, so and how to apply it. So the example, let's say we have just f of x is equal to log of x. What's its derivative? What's f prime of x? So using the rule, it's just telling us that the derivative is going to be 1 over x, that stays, times ln of a. A is the base of the log. If it's not written, we assume it to be, or we know it to be 10. Okay. So this would be 1 over x times ln of 10. And that's the derivative. Any other number, same idea. So if f of x is equal to, let's do ln. What's its derivative? Well, ln of x is equivalent to log base e of x. Okay, it's the natural logarithm. So we can rewrite it as, or if we're looking for the derivative, f prime of x equals 1 over x times ln, and the base is e. And we saw earlier that ln of e is just 1. That's one of our log properties. So this is equal to 1 over x. And this leads us to its own rule. So this is essentially just a special case of this. This is the general form. But we use ln so often that it has its own rule. So f of x, if f of x equals ln of x, and then its derivative, this implies that f prime of x is equal to 1 over x. This one has to be memorized. Okay. And we just saw here why. Okay. So again, this we won't prove until we get to logarithmic differentiation.